Hey folks, so welcome back to another online lesson. This one is on specific heat capacity. Now, most of you who were in the last week of term will have been given a booklet and feel free to use that booklet as a guide. I have changed some of the slides to make it a bit more accessible, so don't be surprised if there are any changes. So let's start the lesson, which is going to be about explaining the difference between heat and temperature. Define specific heat capacity C and use C in calculations. Now, if you find this lesson quite long, feel free to pause it, have a wee break, come back to it. That's the beauty of doing this online learning through this method. Okay, to get you thinking a little bit about this, what happens in the following if you, for example, have a cup of tea in a room or an ice cube in the room? Okay, give you a wee 3-minute pause the video, have a wee think about it and see if you can tell me. Hopefully you answered that a hot cup of tea will always cool down and the ice cube will always melt if both of these were in a room. Now the thing that you might have told me is that the cup of tea would have cooled down until it was the same temperature as the room, then it would stop cooling down, and the ice cube would probably warm up until it kind of reached the temperature of the room and then it would stop changing temperature. Okay, so what do we mean when we talk about heat and temperature and things cooling down or heating up or changing temperature? So heat and temperature have very, very specific meanings in physics. So we're going to do two definitions first of all. And the first one is heat. Heat is a form of energy and it has units of joules or kilojoules. And remember, to convert kilojoules into joules, you multiply by 1,000. Okay, so just writing that down, multiply by 1,000. Now, feel free to write these down on a separate bit of paper or on your notes booklets that you've been given out. It's important for you to write things down so you can make your own notes. Now, you may have seen kilojoules before because if you look at any kind of food packaging, on the back they always tell you how much energy that food provides. So kilojoules might be something that you're already familiar with. And one of the most important rules in physics is that heat always goes from hot to cold. Okay, heat energy, if you leave it by itself, will always go from a hot object to a cold object. And that's why, for example, the warm cup of tea will always cool down until it reaches the temperature of the room, because the tea will be very warm, maybe about 7 to 80 degrees Celsius, and the room might only be 20, 22 degrees Celsius. So that's why heat always goes from hot to cold. And this is one of the key principles of physics. You can't break this rule. So it always flows from hot to cold. Okay, so if heat is an energy, and we know it's an energy measured in joules, what is temperature then? Okay, so temperature is a tricky one. It's the measure of the average kinetic energy of the particles that make up a substance. And you might remember from first, second year that all matter is made up of atoms, and that depending whether they're a solid, liquid or gas, the arrangement of those atoms will be slightly different. And you can see that in my diagram here. Okay, so temperature is a measure of how much these particles or these atoms are moving. It's an average kinetic energy because there are lots and lots of particles, and each of these particles might be moving at slightly different speeds. So instead of talking about all the different speeds, we talk about the average of all these speeds. Temperature has units of degrees Celsius or degrees Fahrenheit or kelvins. Now, degrees Celsius and degrees Fahrenheit you're probably familiar with already because we use that in our everyday language. So if you watch the weather report, you might see that today's weather is 7 degrees Celsius. In America, they use degrees Fahrenheit. Kelvins is a new one, and we'll be focusing a lot on kelvins over the next couple of lessons. Okay, and we'll learn why kelvins is actually a lot more useful later on. So to summarize, you've had the definition for heat energy and how heat always goes from hot to cold, and you've had definition for temperature, and also a new unit for temperature, which is called kelvins. Okay, so let's try and check your understanding of that and apply some physics. So here is a typical question that pupils always pose when they come into my classroom. A pupil enters a classroom after interval and asks to keep the jacket on because they feel cold. Using your knowledge of physics, explain how they would take the jacket off if they want to warm up quicker. Now, this will rely on what we've just talked about with heat and hot and cold. It will also rely on a little bit about insulators, which you have done in first, second year. So pause the video, have a wee think about the answer and see if you can tell me what it is. Okay, so did you get the following as your answer? So first of all, you probably remember that energy always goes from hot to cold. So I'm just going to do H to C to mean hot to cold. Okay, now if you are coming in from the outside, generally the outside is colder, so this would be the outside. So I'm just going to label this as out. And apologies for the rubbish handwriting, but it is very tricky to write on the mouse pad here. And this would be the room. Okay, and the first thing we would say is that hot or heat energy always goes from hot to cold. Okay, so if we think about the classroom being warmer than outside, then the heat energy from the room should go to you to keep you warm, if you like. Okay, so that's the first answer. So the second bit is, well, why should you take your jacket off? Well, the second thing is, remember I said to you about insulators, right? So what do insulators do? And I'm just going to call them ins to make it easier for me to write it. Well, insulators, they trap heat, don't they? Okay, because you know that insulators are very good at stopping heat from escaping from something. Okay, and that's why you wear a jacket to kind of trap your body heat. But the other side of an insulator is that they also stop heat from going into something. So it's a very strange idea, at least it sounds strange. But if you think about it, a thermos flask can be used to keep things hot, but it can also be used to keep things cold, right? Because it stops heat from traveling from one side to another. So if we want the heat energy from the room to go to us, we don't want an insulator around us because that insulator will stop the heat from getting into your body. So this is why you should take your jacket off if you're cold inside. Because by taking the jacket off, you remove the insulator, so there's no barrier for the heat energy to get into your body. And we're assuming the room is warmer than your body, so the heat energy from the room should go into your body. So next time you feel cold, folks, in the classroom, take the jacket off and make sure the heating is on in the room. Now, moving on, because now that we know heat energy always goes from hot to cold, which heats up quicker? So supposing we had a piece of chocolate and a piece of gummy sweet, which one would heat up quicker? And unfortunately, because we're not in the classroom, I can't give you a piece of chocolate and a gummy sweet, otherwise we would. And you could show me which one would heat up quicker. But feel free to do this at home as a wee experiment. Which piece would melt quicker, the chocolate or the gummy sweet? And hopefully you would be able to tell me it's a piece of chocolate. So the question you might want to ask then is, why does chocolate heat up quicker than gummy sweets? What is it about chocolate that allows it to heat up quicker than gummy sweets? And you could ask the same questions. Why is it that some materials like metals feel cold when you touch them, but then if you touch other things like wood, they don't feel as cold? What is it about them that allows temperature, or heat energy rather, to go from one to the other? So this is what we want to try and figure out. And the answer is something to do with this quantity called specific heat capacity, C. And the name really kind of gives it away. Specific means it's targeted at one thing. Heat, because we're doing heat energy. because remember, heat is the thing that flows from hot to cold. Capacity, which means how much it can take in. So specific heat capacity, C, to give a full definition, is the heat energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. And it has units of joules per kilogram per degree Celsius. So for example, water has a specific heat capacity of 4,180 joules per kilogram per degree Celsius. This means to raise the temperature of 1 kilogram of water by 1 degree Celsius, we need to use 4,180 joules. So water requires a lot of energy for its temperature to change by 1 degree Celsius. And this is one of the reasons why we use it in essential heating. So to raise 1 kilogram of water by 2 degrees Celsius, we need to use double that amount. If you do 4,180 times 2, you should get 8,360 joules. And that's because of the units there. It says joules per kilogram per degree Celsius. If you change the temperature by 2, that means you've got to double the amount of energy that you're using. The opposite is also true. To cool the temperature of 1 kilogram of water by 1 degree Celsius, the water would have to give out or lose 4,180 joules, because specific heat capacity works in two directions. One, for something heating up, and two, for something cooling down. And the change in temperature must give out the same energy in both directions. So to cool 1 kilogram of water by 2 degrees Celsius, it would need to lose 8,360 joules. So if you like, it's kind of the opposite of this one here. Okay, so C can work for heating and cooling of an object. Okay, so let's check to see if you've understood what we've been talking about with specific capacity. So given the specific capacity of water is 4,180 joules per kilograms per degree Celsius, now you're not expected to remember that number because it will be given to you on a data sheet. So here's the first one. Try it, pause the video. How much energy would it take to raise 2 kilograms of water by 1 degree Celsius? So the answer was, have we think about it, how much energy would it take to raise 3 kilograms of water by 1 degrees Celsius? Okay, well, if we go back to our definition, you may remember that this is for 1 kilogram of a substance. So if you double the kilogram and you're changing by 1 degree Celsius, it must be 2 times this amount. Okay, 2 times this amount. So it'll be 2 times 4,180. Now I'm just going to rub this out because I do have the answer in this here. It would be 8,360 joules. So to raise 3 kilograms by 1 degree Celsius, how much do you think you're going to have to multiply by? Hopefully you said 3, so that should give you an answer of 12,540 joules. So can you see how there's a very kind of simple relationship here? Don't worry about figuring this out. There is an equation we're going to look at later on to make this a lot more easier. So just to kind of give you a final reminder and a wee summary is that C works both ways. It's the energy given out or the energy taken in by a substance to change its temperature. And if you have 1 kilogram of a substance, it's enough to change the temperature by 1 degree Celsius. Okay, so let's try an example to check that you've understood the concepts, and also if you haven't, let's just to build them up again. So remember, specific capacity is the energy needed to raise one temperature of 1 kilogram of a material by 1 degree Celsius. So let's look at copper, which has a specific capacity of 386 joules per kilogram per degree Celsius. So in other words, if I had 1 kilogram of copper and I wanted to increase the temperature by 1 degree Celsius, I would need to use 386 joules. So let's see how the specific capacity works then. How much energy is needed to raise 4 kilograms of copper by 1 degrees Celsius? So first of all, we're changing the temperature by 1 degree Celsius. So we don't need to do anything more than that because that fits our definition here. But we are increasing the mass by 4 compared to 1 last time. So what do you think we'd have to do with the 386? Hopefully you're thinking we need to multiply it by 4, because remember, the specific heat capacity is only for 1 kilogram of a substance, but we're now using 4 kilograms. And because we're only increasing the temperature by 1, we only need to multiply by 4. So if you work that out in your calculator, you should get an answer, and the units are joules. If you're not sure about that, play the video again and just have a wee think about it. But here's the second example. How much energy is needed to cool 1 kilogram of copper by 3 degrees Celsius? So change things a little bit, because here we're now only using 1 kilogram. So that matches our definition. So we're okay, don't need to do anything there. But we're now increasing the temperature, or rather decreasing it, by 3 degrees Celsius. Whereas before, in the definition, it's only 1. So what do you think we have to do with the 386? Again, we have to multiply by 3. So it's 3 times 386, and remember, it is in joules. But in this case, the energy isn't taken in, it's actually being given out by the copper metal. Okay, so hopefully that gives you a wee bit of understanding with specific capacity. If you don't worry about it. We will look at an equation which makes this a lot more easier to do. So final bit here is apply the physics. The specific heat capacity of certain materials are given. Water has a specific heat capacity of 4,180 joules per kilogram per degree Celsius, which you know already. Copper, 386 joules per kilogram per degree Celsius. And aluminium, which is 902 joules per kilogram per degree Celsius. So here's a question for you. A heater provides 5,000 joules of energy. Which material heats up the most? Okay, so you can do a wee bit of rough working here. You can pause the video and try and figure it out, look through what we've done before. I'll give you a wee hint here. Another way to word this question would be, which material changes the temperature the most? Right, so think about how much energy you've got and how much it takes to increase the temperature by 1 degree Celsius. You can assume, to make this easier, you've got 1 kilogram of each of these materials, and see if you can figure out which one is going to heat up the most. Okay, I'm going to leave you there, and I will continue the lesson on Wednesday when we look at how to use specific capacity in calculations.